We have seen the momentum and position representation, and now we are trying to get the connection between the position and momentum representation. Now when changing from the momentum means from the position, so this is our position base, and this is our momentum base gets. Now changing from this position basis to the momentum basis, we need a transformation function. We need a transformation function. So this is what we required to connect these two things. Now to find the expression for the transformation function, so let's establish a connection between the position and momentum representation of the same state vector psi. So let's take the inner product of this state vector psi in the position base. In the position base, this can be written as, what we are doing is we are going to introduce an identity operator just before this psi ket. So this will be integral. Now we are going to introduce an identity operator in momentum representation. So this is dqp p. So this is an identity operator. Then we have psi. See, this is an identity operator in momentum space. In momentum representation. Okay. So this is, we have seen previously that this is given by psi of r. The wave function or the projection of the psi onto this position vector or the position basis. So this can be written as integral d cube p. Then let me rearrange above expression, so that will give us r p. And then yesterday we have seen that this thing, the projection of the state vector psi onto the momentum basis, is given by capital psi of p. So this can be written as capital psi of p. Okay. So similarly, you can write, or you can take the projection of psi, the same ket onto the momentum basis. So this will be bra p and you get psi. Then this is what we write as capital psi of p. Okay, so this is given by integral d cube r. Similar to this expression, for momentum you can write it in terms of position representation. So this can be given by integral d cube r p r, then small psi of r, which is the wave function. So we have two equations. Let's say this is our equation 1 and this is our equation 2. So we have from these two equations, you can see that this psi of r and psi of p, they can be considered something as the Fourier transforms of each other. The Fourier transform of a function f of r in quantum mechanics is given by the expression f of r equal to 1 by 2 pi h cross raised to 3 by 2 integral d cube p e raised to I p dot r by h cross g of p. Now if we set in equation 1 and 2, if we set r p in equation 1 as e raised to I p dot r, then equation 1 which looks like a Fourier transform of the wave function. So if you set this, equation 1 will be the Fourier transform of wave function, the Fourier transform of wave function psi of p in momentum space. So what is our equation 1? So this is our equation 1. Now you can see that with this set, you can see that this will looks like equation 1 looks like exactly looks like a Fourier transform of psi of p in momentum space. So it will look like this. With this transformation, you can write it as psi of r equal to integral d cube p e raised to I p dot r psi of p. Now this is not quite a Fourier transform, since we have the momentum p rather than the wave vector k in the integral. However, what we do is we use the de Broglie relation connecting k and p, which is given by k is equal to p by h cross, or p is equal to h cross k, right? With that, you can consider this function rp as 1 by 2 pi h cross raised to 3 by 2 e raised to I p dot r by h cross. So this is what we take this transformation function rp. Okay, so this function transforms from the momentum to the position space. So it gives a transformation from momentum to this position space, and we have identified that as something similar to a Fourier transform. So we have seen that this connection between the position and momentum representation almost looks like a Fourier transform. So we have identified this transformation function as something like this: 1 by 2 pi h cross raised to 3 by 2 e raised to I p dot r by h cross. Now the function corresponding to the inverse transformation, we can consider p, so which is the inverse of this above expression. So this is basically rp star, right? So this can be written as 1 by 2 pi h cross raised to 3 by 2 e raised to minus I p dot r by h cross. See, with this transformation, actually you can write psi of r equal to 1 by 2 pi h cross raised to 3 by 2 integral d cube p e raised to I p dot r by h cross and psi of p. And with this one you can write our equation 2 can be modified as psi of p equal to 1 by 2 pi h cross raised to 3 by 2 integral d cube r e raised to minus I p dot r by h cross psi of r. So now these two looks like exactly the similar the Fourier transforms of each other. So what this quantity basically represents, this quantity, if you consider this rp modulus square, it represents the probability of finding the particle in a region around r when its momentum is equal to p. So it's basically the probability of finding the particle in a region around r when its momentum is p. And now let's see how does the momentum operator looks like in position space. So we have seen how to connect one representation with the other one. If we have something in momentum space, that can be easily converted into the position space using the transformations equations that we have seen just before. So how to represent a momentum operator in position space? So for that let's consider this transformation function rp, which we have just seen now, and this is we have seen that is given by 2 pi h cross raised to 3 by 2 e raised to I p dot r by h cross. And we have also seen that the momentum operator acting in momentum baskets will give us the momentum eigenfunctions. So these are the eigenfunctions of this operator capital P. So in momentum space, the momentum operator acting on the momentum eigenfunction retains the momentum eigenvalue times the original momentum eigenfunction. So that means in its own space, the momentum operator is a multiplicative operator. So the same is true for the position operator in position space. Now to obtain the momentum operator in position space, this expression can be projected onto the position space by operating on left by this bra r. So what we are doing is we are going to project these things into the position space. So for that, what you have to do is multiply it with r. So this is equal to the momentum eigenvalue p. So if we make substitution for rp from above equation, this will be 1 by 2 pi h cross raised to 3 by 2. Then we have this momentum. Then for rp you can write it as raised to I p dot r by h cross. So now let's consider, let's keep it there and let's consider some function, let's say f, which is equal to e raised to I px into x by h cross. So this is basically what I have considered here is this part, the uh, one-dimensional form of this exponential, let's say e raised to ipx into x by h cross. So let's put it as some function like f. Then let's differentiate it with respect to x. So d by dx of e raised to ipx into x by h cross. So this will give us ipx by h cross into e raised to ipx into x by h cross. So this is basically ipx by h cross into f itself, because this is f itself. Or if you rearrange this expression, you can write it as px into f and take all other terms to the left side. So that will give us minus ih cross d by dx of f. So when you take this I to the left side, that will go to the denominator. So bringing it to the numerator will make it negative. So with this we can write p into e raised to ip.r by h cross equal to minus ih cross. So in three-dimensional form, if you consider in three-dimensional form, this can be written as minus ih cross. Instead of d by dx, we write the gradient operator considering all x, y, z coordinates. So this is del of e raised to I p dot r by h cross. So with this we can write this expression r p and momentum p. This is equal to 1 by 2 pi h cross raised to 3 by 2 and then multiplied by I h cross del e raised to I p dot r by h cross, right? So this is same as minus I h cross del. Now all these quantities basically this one and these two, this is basically our transformation function, which is given by r p, the connection between position and momentum space. Or you can write, if you remove the momentum from both sides of this expression, you can see that this r p equal to minus ih cross del r. So this gives you the idea that in place of this momentum operator, what we have on right hand side is minus ih cross del. So we can write it as the momentum operator is equivalent to minus ih cross del of r in position space. This suffix r means this is with respect to x, y, z variables. The differential is with respect to x, y, z variables. So in component wise, the operator px can be written as minus ih cross dou by dou x and py, the component of the operator py can be written as minus ih cross dou by dou y, and pz can be written as minus ih cross dou by dou z. Now the position wave function in momentum space is the complex conjugate of the momentum wave function in position space. So this p r is same as rp star. So this is 1 by 2 pi h cross raised to 3 by 2 e raised to minus I p dot r by h cross. Now using the procedure outlined before, we can see that the position operator in momentum space is given by the position operator in momentum space. So what we have, when we have the position operator acting in the position baskets, that will give you the position eigenvalue times the same baskets. So if you do the same procedure what we have seen before, the position operator can be identified as something similar to IH cross del P. So del P means the derivative you have to take with respect to the momentum components, d by dp instead of d by dx. Okay, so this is an exercise, so you can use the procedures that we have done to show this expression. So you use the same procedure with this momentum operate with the position operator in position space, and then you what you have to do is you project these things basically to this momentum space and see how is it working. So you have to prove it.